So now that we start to understand that like functions can be a little bit more tricky, and not all equations are functions, we want to start getting into going back and challenging some of the other things that we took for granted, like limits. Limits, again, we always want to have some friendly wording that goes along with limits. What's a good friendly word that goes along with limits? What was it? Slope would not be for limits. We do use limits and slope to make derivatives. Absolutely. Range talking about how high a graph can go or how low it can go. It does have a little bit of something to do with infinity. We've looked at moments where I have something going towards infinity. That's one context. And then somebody said the magic word over here. Approach. If you want a simple word for limits, limits are the logic of approach. So we can approach infinity. Great. We can approach slopes with other slopes. Great. We call those derivatives. We can approach filling area with other areas. Great. We call that integrals. Like we've got limits are at the core of calculus. They are literally the calculus idea. Limits and the ability to do logical approach is the calculus idea. Then we take that calculus idea and we apply it to a bunch of scenarios. We apply it to slope equations and get derivatives. We apply it to area equations and get integrals. We apply it to functions and we get horizontal asymptotes, vertical asymptotes, you name it, whatever. But limits is just simply the logic of approach. So the thing we want to explore today, because as mathematicians, our job is to break things. I once heard engineers, their job is to fix things. I used to be an engineer, I can relate. Mathematicians, their job is to break things. We're going to be looking for those times when our logic of approach is not as simple as we might have thought. And we're just going to explore a couple of those instances in class, but they are very, very interesting instances. And I can get you some real world examples of the applications for them if you'd like. Although admittedly at this point, it is going to be a little bit sparing on the applications because we're just trying to break it from a math standpoint because we want to understand it deeply, not because we have a question in front of us. But then we will eventually bring questions back that are dealing and pertaining with the real world. Okay, a little bit of an eyesore. If you got the guided notes, you can follow along. If not, you've already written this all down. You don't got to write it down again. This is just a remembering of how we developed the definition of limits. So we started off with trying to say if it's the logic of approach, then we can say that an expression has a limiting value, a limit. If I forever approach that number, give me a general nod if we remember that storyline. All right, so limits are the idea of this forever approach. And then we said, okay, but from a purely rigorous standpoint, there's some difficulties we have with that. Like, what if I approach two things, like those plus or minus square roots? And we said, well, that's not exactly what we want. We really want it to settle in on one. So we said, okay, let's make sure that's explicit. Let's make sure we understand we are settling in on one value, one limit per conversation. Okay. So then we rewrite that. We say an expression has a limiting value or a limit if it forever approaches a single number. So we adjusted our definition. We tried to break it. We improved it as a result of trying to break it. We go back, we challenge again. The challenge this time is what does it mean to forever approach? Like that's pretty easy to talk about conversationally, right? 0.9 and then 0.99 and then 0.9 repeating more and more and more and more gets closer and closer and closer to 1. And so I can say that that idea is that I'm forever getting close to 1. But when you actually pin it down and I say, who got to the forever and double checked for me? Like forever is not something we can do easily. Forever is not something that I can finish. So we don't want to say I forever approach it and then have absolutely no mathematical standpoint to be able to say, yeah, I confirmed that. So we say, okay, how can I capture this idea of forever approach without actually having to do the forever amounts of work that would be necessary to show that I have forever approached? We say, okay, well, here are some ideas. Maybe we could instead talk about it as looking to see if it's different. So that's kind of where we got our formal definition. So our formal definition, the limit of a sequence, so a sequence is a list of data. So we could say like 0.9, comma 0.99, comma 0.999, that I can make a list. And that the limit of this list exists if a number in this sequence can always be found such that afterwards, a number is within some desired tolerance. In other words, if I claim that at the end of this list is the number 1, then I should be able to have a discussion with you. And I say, I believe that the limit is 1. And you say, I think it's something else. And I say, well, I can show that we can get really close to 1. And you say, well, what does really close mean? I say, I can get as close as you ever want. Because I could find a value. You might say, I need to be within 1/1000th of 1 to believe you. And I'd say, no problem. I can cut my list here, and all of those values will be that close or even closer. And you say, never mind, that was too easy. I'll make it 10,000th, 1/10,000th. And I say, no problem. I can find a place in my list where I cut it, and all of that data after there supports me to within your tolerance. And you say, never mind, I need to make it even more. And I say, it doesn't matter what you make it. I can always find a point on this list where I meet your definition of close enough. And you say, oh, so then that must mean you forever approach. And I say, that's what I've been saying. I don't actually have to get to the end of forever. I just have to convince you that I could always find a place that meets your definition of close enough. And because I can do that for anybody and any question, we've captured the idea of forever without actually having to get to the end of the ... So I've got plenty of time in this lecture to really kind of talk through these issues, these details. Does anybody have any questions about where I'm pulling that definition from or how I'm using it? If it helps, sometimes I find a picture to be worth 1,000 words in this case. For example, we have been doing limits as x approaches infinity. Let's look at a graph I could do, nothing in particular, just maybe the one that came up on the exam. Let's talk about this one here. So the limit as x approaches infinity of this curve would be what? -2, how come?
Moving to the right.
So we're growing, x is growing and growing and growing without bound. Yep.
And it's like an arrow, like a glowing -2.
Does it ever get to the -2? So do you all notice, like at that point, I could be like, then how do you know? It never actually gets there. What would your counter argument be? It's close? What do you mean by close? What do you mean by approaching? I like close. Go back to close. What do you mean by close? It's close, right? Anybody else see that it's close? Do you all think that you're all looking at the same amount of close, or are we all recognizing that if I continued to look at bigger and bigger x values, that my height would just be closer and closer to -2 the further I go along, right? So what you're saying is if I gave you my definition of close, you could meet it. If I said, I need you to be within 1,000th to believe it, you said I could come over here, you could be like, right there, I'm going to cut it off and look all over there. Look at that tiny gap. That's close enough. Like that's within your close. And I could be like, never mind, I want to make it tighter, right? Really close. And you say, no problem. I could find some place that would meet that close because it's going to always be able to be found to meet that close because it's always getting closer. So that's how we defined limits. We said that I can cut off this data at some point and everything afterwards meets any definition of close. And we just have it as a cyclical recipe where whatever you want close to be, I can give you a recipe that goes and finds that. All right, give me some thumbs. How are we feeling on that approach? We're feeling pretty good? Okay, nice. So let's again look at this with some data. I'm just kind of revisiting, we're reinforcing. I'm hoping a lot of this feels like review. It should, like that's the whole point of how I structured the class, is that it should start to feel a little bit like review and we're just picking up details we might have missed on the first go around. So let's look at this, for example. If I have the limit as x approaches 2 of x squared, what do we think that will be? Limit as x approaches 2 of x squared. Go ahead.
4.
Tell me why.
4.
So are you saying that you're considering the approach or you're considering plugging it in?
Honestly, plugging it in.
Honestly plugging it in? Good. But notice that the moment you plug it in, you're not doing approach logic anymore, unless you can connect those dots for me.
Well, if you go from, say, 1.5, I don't know, that gets pretty square. But if you go from a number that's not 2, that's lower than 2,
Mhm.
then you're never going to be above 4. You'll never get above 4. But then if you go past 2, you will surpass 4.
Okay, so you're kind of looking at it as like that data nearby, but you're connecting that like I go closer and closer to plugging as if I was plugging in 2. And had you been able to plug in 2, it would have been 4. So that must be the limit either way. I love that. That's really good logic, right? That's a really nice explanation. Because there are times where we will get the same thing if we plug it in. Like plugging it in is not bad. Plugging it in just requires that you tell me why that's allowed. And if you say, because I'm gradually getting closer and closer and closer, so I'm allowed to plug it in there, I say that's good. Because that's the definition I'm looking for. I'm looking for the closer and closer and closer part, and I just need you to connect those dots for me. So that one's really nice. Now, the only thing I would say is, why do we need to approach from less? Couldn't we also approach from more? For example, if I plug in 2.1, that's going to be close to 4. If I plug in 2.01, that's even closer to 4. 2.001, that's even closer to 4. In fact, I got some data here, right? If I start bringing in from the above, the x values come closer and closer to 2. Take a look at these y values. Don't those come closer and closer to 4? And I get that from below. So from the data standpoint, it seems like it shouldn't matter which way I approach, which I feel really good about, because again, we should be landing on one single limit. If I have the opportunity for 2 different answers, that's not what we're talking about. So I like this. I also recognize that the method of approach doesn't matter. In other words, if I give you a different table with different values that still capture the idea of approach, I should still land on that same value. Like below here, I've got a different table, but notice that these values still get closer and closer to 4. That's great. And then we can maybe ask ourselves, we could go back to the graph. We could say, I know what an x squared graph looks like. An x squared graph looks like this. And I know that above x equals 2, I have a height of 4. Even though it's not asking me for the height, I know there's a height, but I can again justify that I could say, as I approach 2, I approach the height at 2. Because this is a graph of steady and gradual change. So it doesn't matter which of these are all great arguments. Either I can justify that I have steady and gradual change towards a height of 4. I can verify that with my data and any data that I could possibly imagine getting. And because it's slow and gradual change and no interruptions, I could say it's also going to be what I get when I plug it in. Good. Very nice. We all feeling good again? Nice. Again, a reminder, hopefully a nice refresh. Cool. So this is where I've kind of been writing like that idea of saying I've got the logic of approach. And in my math, it doesn't always show the full discussion that we are having out loud. But nonetheless, I really want to stress to you all that if there's ever a time when you stop writing that limit notation and you plug it in, you need to have a really good reason. Like it's not always going to appear on the paper, but I'll be able to tell through your notation whether or not you actually considered the data that was along the way, or if you just kind of replaced X because that's what your muscle memory tells you to do. So make sure that we've always got that logic of approach that's backing up any ability to plug things in, because we're about to break it. We're about to find out that there are times where you can't do that, and we need to be careful. So let's take a look here. I've got an example, again, a graphical one. Let's take a look at some of the different notation and remind ourselves which of these is algebra questions and which of these are calculus questions. So for example, let me get somebody who can help remind me what this is and what it means. Please. Okay, so F is the function. Tell me about the parentheses and the 2. Good, so it's saying what is the height, the y value, above the x value of 2, right? So now help me out with that. When I go over to 2 and I look up to my function value, what would that be? It would be a height of 2. Do we all agree, right? That is the only place that there is a y value above x equals 2. So that's going to be 2. That feels good. This right here, algebra question, right? Algebra question said, what am I above 2? We plug in 2, we get above 2. That's algebra. Good stuff. Let's now take a look at this one. Who can tell me what this is as a story, as a sentence? Bounce it around. Use as few math words as possible. If it helps, ask yourself again, what's the nice word for limit? Approach. So somebody help make that a sentence for me. Go ahead. As x approaches 2, what do I expect my height to be, right? So that works out pretty good. Now, does this tell me how I'm approaching? No. So I'd better be pretty general in any way that I try to collect the data. I better be trying to consider other perspectives besides mine. Well, I could approach 2 from a little bit above. I could come at it from heights that are from x values that are slightly bigger. If I did that, then I've got x value, x value, x value, x values all the way on in. And above that, I've got a place on the graph where I have height, 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 height that correspond. So as I bring my x values in towards 2, it looks like my height is dropping towards 4, right? As I bring my x values on in, I've got a height here, I've got a height here, I've got a height here, and all of those heights are coming in towards 4. Let's look at it from the other direction. Let's imagine I was collecting data from a little bit less. Then in those cases, I would be a little less, more closer, 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 closer. And then above those, I would have a certain point that has height, 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 height. Approaching what? 4. So if I said conversationally, what are the y values approaching as x gets close to 2? You would all say 4. And it's just like that. Notice again that we're still supporting this idea of having a list of data. We're still collecting the list of data, and we still have the ability to say, I want to get close, whatever you want close to be, because then I'm just going to say, okay, if you want to get this close in terms of height, then I'm just going to get this close in terms of x, and I'm kind of cutting everything off to the sides and saying close enough to x gets me close enough to the limit I see. Go ahead.
So it's 4 because its approach is 4, but it never gets to 4 because if it did, then it would actually be 2.
See, it's not about did I get there? See, did I get there is a conversation, is a question that's perfectly legitimate, but it's an algebra question, right? What is my value above 2? That's a great question. I love that question. Then there's another question that says, what did I expect to get as I approach 2? That's also an equally good question. As we can see here, the answers to both questions are different. Here's my favorite example. Have I all told you about going down the staircase in the middle of the night story? Oh, here's my favorite example. Anybody here ever go down a staircase in the middle of the night? You think there's going to be one more stair, you hit the ground, you stumble? We all remember having that experience, right? So let's all kind of think about what's happening there. That's 2 parts of your brain, both doing good logic. One part of your brain is saying I was on a stair. I'm currently on a stair. The next thing is going to be it's going to be a stair. And then the other part of your brain goes, oh, dang, that's a floor. Does that mean that you were wrong for your logic? No, your logic was perfectly fine. I was on, I am, I should expect. Expectations are great. Anybody here planning to do something this weekend? Anybody got plans for the future? Maybe what you're going to have for dinner tonight, right? Like plans are logical. You can have plans. Plans are fine. Just to say that the plan is not what we got does not mean that you are stupid for making plans. It just means it's a different conversation. We can have plans. We can look at approach. We can have thoughts about expectation. Whether or not that's actually what we get when we get there is not the conversation. So here we expected, as we traversed along this, just like walking along a staircase, we expected to get a height of 4, just like walking along that staircase. The fact that there was no stair there and that instead it dropped out from underneath us does not mean that we expected differently. It just means that it wasn't actually there. So it's all about what the question's asking. What should I expect versus what is? Sometimes they're different. What about this one here? F with parentheses and 0. Somebody tell me what this means using as few math words as possible. Let's again try to bounce this around. Use this as a chance to practice your language. At 0, what is the height? Give me a nod if we all agree with that. Feel pretty good? Excellent. Good. Then let's do it just like that. Am I approaching 0? Didn't say anything about approaching 0. It said at 0. Good. I'm going to start right here at 0. I'm going to look up. What's the height at 0? 2. Excellent. Good. Good stuff, right? Somebody tell me what the next one is asking. Good.
As you approach 0, what's the height?
As you approach 0, what do you expect? Right? What do you approach as height? So you can think of that as like, what do you expect? So as we approach, now I'm tracking along. What did you expect as we tracked along the graph? What do you expect the height to be? To be 2, right? Because we can watch it just like a staircase. I'm walking along it just like a staircase. From one direction, I expected a height of 2. From the other direction, I expected a height of 2. That means that my expectation was a height of 2. Did it matter that I actually got there? Not for that conversation. But as it turns out, I got there and I expected it, versus on the other example, I did not get there. I got something else that was different than my expectation. So it's almost like I will get what I expect so long as I am not disrupted, so long as there's not a break, so long as there's not an interruption, which means that sometimes I will be able to solve limits by plugging in values. Sometimes I won't. The times I can will be times where I am not interrupted, where there's not a sudden change, a sudden disconnect. Go ahead. Cool. So let's take a look here. If I now say that I've got 2 different ways of approaching, let's see how that comes to be. Like, for example, if I'm talking about this function, let's remind ourselves that we have piecewise functions. Piecewise functions, again, are a fantastic way of modeling the real world. They're a really good way of being able to capture multiple mathematical models into one storyline. Here, this says that I have a function titled h, and it depends on t. Maybe we could think of that as time. And it says that for some times, the times that I am less than -2, the height of this graph is at -1. And the other times it's going to be at 2, which supports the picture below. So let's take a look. What do we think will be the limit as x approaches -2? Oh, sorry, not x, t. As t approaches -2 of h of t. Well, we're going to imagine that just like I'm walking along a storyline, right? Go ahead.
It depends on if you approach it from the right or the left.
It depends on if we approach it from the right or left. Let's see if we can take a look at that one, right? As we're approaching it from the right, I have a height of 2, height of 2, height of 2, height of 2, height of 2. I expect my next height to be 2. So I've got from the right, I think it will be 2. From the left, I think it will be, well, let's see, I have a height of -1, -1, -1, -1, -1, -1. I think it will be, everybody help me out. -1. So what is the one value it approaches? Because keep in mind, if we go back all the way to how we defined this thing, single number was an important detail that we already thought of and we already classified for. So I'm coming down here and I'm seeing that depending on the approach, I've got 2 values. So what is the one value I approach? Who said that? That was great. There is none, right? If I say, give me one answer and you can't, then you can't give me one answer. Right? So if I say, what's the limit? And you say, there is not one limit, then I say, then the limit doesn't exist. And you're like, yeah, I guess so. So what we want to do is we want to try to make some notation that captures this idea of how did we approach? Because sometimes if we approach different things, we want to show our audience that that's why there's not a single value. So what we do is we come up with something for from the right. Well, from the right is not very mathematical. It really requires that we have a graph in front of us, that we're talking about something with our eyes. Really what we're looking at from the right is we're looking at x values that are a little bigger. Do we all agree? A little more positive? So we could make this, well, people do write it as the limit as t approaches -2 from the positive. A little plus sign as a superscript. This can get pretty confusing because we've got a lot of symbols flying around the paper. Here is my recommendation to help kind of ease some things in your notebook. I like to put parentheses around the -2 if I'm confused. That way it really forces me to read this as the proper sentence. T is approaching -2 from the positive. So that means things that are a little bit more positive than it. So if we wanted to use this notation, the limit as t approaches from -2 from the positive would be what? If you need to, track it along with your finger, right? We're coming from the positive direction. Think about the heights along the way. What would we get? Good. We'd get 2, right? That's literally this storyline right here. If I wanted to do the limit as t approaches -2 from the negative, again, maybe some parentheses will help organize our thoughts here. That would have been our -1. And then we would say, because they didn't match, there is no single limit. Oh, great. Then we can start to actually structure all that like a sentence. Okay, so let's go ahead and we'll clear a little space here and let's start to structure all this because we can write this in a way that our audience, no matter who they are, can follow. Let's try this on for size. Since the limit as t approaches -2 from the positive of h of t, notice I didn't just write lim equals. Lim means get a list of data that support what we approach. It does not mean limit, right? Lim means forever long list. So we want to say forever long list of what? Of h of t, of our function. So since this here equaled coming from the positive was 2, and the limit as t approaches -2 from the negative equals -1, and the limit as t approaches -2 from the negative of h of t does not equal the limit as t approaches -2 from the positive of h of t, then the limit as t approaches -2 of h of t overall is what? Again, we got to decode the language. We said that from one direction we got one value, from another direction we got a different value. So the one value they both approach is
Undefined.
does not exist. Very nice. All right, there is no single value they approach because from one direction I got one thing, from the other direction I got something else, and they don't match. That's literally what we've just written here. It's at this point that we start to recognize that the class is not so much about like plugging in numbers and getting values. It's almost like you're making an argumentative essay for me, right? It's almost like you're trying to convince me of all the logic you saw, all the reasoning you had, everything that you did to support your conclusion, as if I don't already know what you're talking about. And that's exactly the point. You have to walk your audience through. What did you consider? What did you find? What does that match with in terms of what we're talking about? And what's your conclusion? And we list it all out just like this, like sentences and stories. Good. Let me pause here for a moment. Does anybody have any questions? All right, we're feeling okay. Let's take a look at a few other examples, really start to get this thing ironed in. And we're going to take our time with this one because it's about all that I've got. After that, I've got a little bit of discussion for recap, and then that's about it. So really, this is the thing to focus on today. So again, let me try to bounce around. This is a really good opportunity. I know it can require us to kind of put our humility to the side and be vulnerable as we try out this language, but I'd like y'all to give it a shot. Somebody try, if you would. Tell me what that means. Give me the sentence behind the symbols. That's really the difficulty of this section, is just trying to make sure that we understand what it's asking for in the first place. Yeah, go ahead. What is the height of the graph when x equals -4? Do we all agree? Give me some general nods if we feel good. All right, are we approaching? We are not approaching. This is an algebra question. I don't need any approach. I don't need any calculus. This thing just literally says, what is the height above -4? If we look, go ahead and carry it through. What's the height above -4?
There isn't one.
There isn't one. So if I say, give me a number, you say I can't. In other words, does not exist, right? Again, sometimes it can help if we have like a physical motion to do with our pencils or pens, like I'm going from -4 up. There is no in, there is no close, there is no approach. This is above. And so we just try to walk that down. All right, somebody else. Let's bounce around a little bit. Let's try this one. And again, the fact that I'm kind of moving slowly by calling around gives you all an opportunity to literally be writing sentences next to the symbols. Right, this is what I mean by saying put your brain in your binder. Yeah, go ahead.
Yeah, what is the height of f of x as x approaches 6 from the left side?
Very close, good. I would add in what's my expected height, right? A little, just because the expected again reminds us, I don't actually need to have it. I just need to figure out what was I approaching forever and ever. So we got, as I approach from the negative is going to be from the left or from the right?
The left.
From the left, from the more negative stuff. So I'm going to be over here. Here's my 6. I need to be approaching it from the negative. So at those moments, I'm grabbing x values closer and closer and closer and closer. Each of those has y values closer and closer and closer and closer. As we track along that, what do we expect that height to be?
You'd expect it to be 5.
We would expect it to be 5. And that's how we work it through. Does it matter that I don't get there? Did the question ask what I got? No, the question asked what I expect, right? So it doesn't matter if you actually get it unless the question is asking you for that. It's always about what do I approach, because limits are the logic of approach. This is where we're really trying to break things and work through the weeds. Like, we want to understand that the logic of approach is different logic than the logic of is, even if they overlap sometimes. Fundamentally, they are different questions. All right. Let's bounce around to this one. Oh, you got a question? Go ahead.
So if you could approach from the top, one of the answers still be the same?
In this case here, so we're saying we want to make a different statement, like let's consider limit as x approaches 6 from the positive of f of x. All right, make your case.
Because you're approaching from like the top, so wouldn't it also like hit 5?
So what do you mean by approaching from the top? Are you tracking along the graph?
Yes.
Okay, let's make sure that we're starting with tracking along with the x values, but I like that you're kind of looking at that as heights that track along the curve. And then you're saying that the expected height would have been 5. So tell me this, if I think I'm going to get a height of 5 for my limit from below, and I expect a height of 5 with my limit from above, do I have a limit that we agree on?
Yes.
So does the limit exist? Is there a single value that everything approaches?
Yes.
Absolutely, right? So in this case, we can actually say, since the limit as I approach from above equals the limit as I approach from below, and both of those are 5, then the limit as x approaches 6, regardless of direction, is 5. Right? Because it's just asking, what did I expect to get there? Again, I didn't get it when we actually look, but that's not the conversation. The conversation is asking, what did you approach? What did you expect as you got along that approach? Good. Let's go back to this one. F of 1. Again, this is a good chance. If you haven't participated yet, like, give it a shot. Start structuring that language. You want to give it a shot?
4.
4? Tell me why. Give me the full story walkthrough.
That's because as x approaches,
Be careful. Are we talking approach for this one?
sorry, for the given value of x
Mhm.
equals 1.
Yep.
Your outcome is 4.
There you go. Very nice, right? At x equals 1, the function's height is 4, right? So we kind of got this at and is language that goes along with the algebra questions. And we've got this approach and expect language that goes along with the calculus questions. So good, very nice. Right at x equals 1, there's only one function height. It's right above it. That height is at 4. So my height above x equals 1 is 4. I should note again, I'm using the term above loosely, right? I just mean like the height at x equals 1, whether it's above or below. It's just the function value, the y, the output. Yeah.
Why would you not -2?
You tell me. Is that the height? Like, is that the function value that we get if we look at x equals 1? Yeah. because there's nothing there, right? So it'd be difficult for us to say that the height for x equals 1 is -2 if there's no height there. So those circles can remove specific data from being our possible answers for algebra questions. Good, nice. All right, let's bounce to, what should we do next? This one? The limit as x approaches 1 of f of x. First, how are we approaching? Exactly right. If it doesn't specify, then we just need to keep it as approach. All approaches, any approach, any disagreement breaks our trend. We're talking about just approach, all approaches, anyone's interpretation of approach. So in that case, as I approach x equals 1, I need to be a little bit below, I need to be a little bit above. Let's start with the above. If I go above x equals 1, then the heights that correspond here are going to be these heights. And along that approach, we think that the limit will be what? -2. From the other one, we get a little below, and we get heights that approach 4. So what is the limit I approach? It does not exist, right? Because there's not one single value that I can pin down and say, this is what I approach as x narrows in towards 1. So this one also does not exist. All right, I'm gonna leave it all to you. Who wants to try, like you pick one. You pick one of the remaining ones, whichever one you feel most comfortable answering. Do it Jeopardy style. Good.
I don't want to do the bottom.
The very bottom one?
Yes.
All right, walk me through the language and the thought process.
All right, so it's asking you what the expected value is approaching 6 from both sides.
There you go, right? So we're gonna approach from both sides. X is gonna get nice and close in both approaches. If we're looking for that as we are getting heights, those would be heights along the curve here and heights along the curve here, and that would be 5. Oh, in fact, like again, if we wanted to justify it, remember that's what I've got written up here. This is the full justification. This is exactly how we would convince an audience member if we had to write to them through a test or a written homework response, right? You'd have to specify all of it. I checked the left, I checked the right. They both agreed, so therefore the limit is. We've got to make a full, nice argument. Very nice, good. All right, we got 2 more. Who else can help me out? Again, if you haven't tried, give this a shot. Go ahead.
I'll do the second to last one.
Second to last one. So first, read to me what that is saying.
So that's saying, what is the height of x as it approaches -4?
Close. What is the, so as x approaches -4, in general or specifically one way?
From the right.
From the right. So specifically as x approaches -4 from the right, that's already way too much for me to keep in track in my head. So I'm going to try to put down the paper. As I approach -4 from the more positive, that means I'm tracking this way. All right, take it from there.
We'll reach at 2.
All right, so then we say, what do I expect my height to be, right? What does the data in my approach support? So I'm tracking along these heights, and you said the expectation would be 2. Right? Again, if that negative and positive stuff starts to get confusing, I recommend you do parentheses. The parentheses will force you to put parentheses in a place that you recognize what that means, right? Because none of you have ever written that before in your life, right? So if all of a sudden you visually pull that apart and you go, that's what I should focus on, you're going to catch that that doesn't look comfortable. However, if you write this, this will force the storyline if you give it a chance, right? I'm approaching -4 from the positive, like it forces the sentence structure for you. So I highly recommend it if you're having trouble. All right, somebody else help me support this last one. F of 6 means, yeah, please. The height when x is 6, that would be what? It would be 2. I would have thought it'd be up here. Tell me why it's only 2. Very good, right? Because there is no height there. There's a gap. There's an open circle there for a reason to say that is not the height, right? So absolutely, we're going to look for where it is. Notice it doesn't always match with where I approach. Sometimes it does, sometimes it doesn't. It's fine if it does. It's fine if it doesn't. They're different conversations. So now let's see if we can draw a little bit of a preview for what we'll talk about next class. When are these things matching and when are they not? Right? Like, for example, here, we had f of 6, very different from limit as x approaches 6. We had f of -4, very different from what my expected height was as I approached -4. Who can kind of capture the y? Yeah, go ahead. Okay, so maybe it's better than for, instead of us trying to say when are they the same, we instead ask when are they different? And they're different when what I approach is not there. Right? If what I approach is not there, then my algebra will not match my calculus approach. So we've got a descriptor here. If it's not there, if I am in an interruption state, if I am not able to continuously sketch this curve, then I have a break. We're going to formally define that word continuous next time, but take a look here. If we go all the way back to this one, limit is x approaches 2 of x squared. Did we expect the same thing from above? In other words, things that are a little bit bigger than 2, if we plugged it in, did we expect them to get closer and closer to 4? From a little below, did we expect it to get closer and closer to 4? Was there agreement? Was there therefore a limit? Did it also actually exist? And if we look at the graph, was there ever an interruption? So now we understand those times that we've been doing those past problems where you've just been able to plug things in, those have been only able to be plugged into problems that have no interruption, that have no discontinuity. If they do have a discontinuity, that's going to be a time that we won't be able to plug things in. And it's actually something you've been playing with for quite a while. We'll talk more about that next class. If you have any questions, feel free to stick around.